afternoon, everybody. It's my pleasure to introduce our very own Tristan Bice. We'll talk about massive Pierce duality between ample groupoid bundles and Steinberg Morphism.
Well said. Okay, thank you for the intro, Karen. So, yep. As Karen said, I want to talk to you about some dualities I've been playing with recently between certain kinds of algebraic structures, certain rings, and certain more topological structures, so topological spaces and bundles. So just a bit of history to begin with. So there are quite a number of dualities of this form which you may have heard of between commutative rings or algebras on one hand, and more topological structures like topological spaces or bundles of spaces or bundles of rings over some kinds of spaces. So one of the most famous, one of the classical ones is Gelfand. So he showed that commutative C-star algebras are essentially dual to locally compact Hausdorff spaces. So given such a space, you look at the continuous complex valued functions on that space vanishing in infinity, that gets you a commutative C-star algebra. And what Gelfand showed is that, in fact, all commutative C-star algebras have to be of that form for some, up to isomorphism, right, for some space. Well, I think Gelfand was really the one in 41 who did this one. Gelfand-Nightmark is for the the GNS construction on representing operators on a Hilbert space. But just this part, I think, was really just Gelfand. People refer to it as the Gelfand duality anyway. Yeah, so that's the one which I think Nightmark was involved in. This, I think, was just Gelfand, right? But, yeah. Another one which is maybe not quite as well known, it's sort of an algebraic version of this. And it just says that if you have any commutative ring, as long as it's generated by its idempotents, then again, you get this duality with zero-dimensional compact Hausdorff spaces, generally known as stone spaces, and we'll see why very shortly. So yeah, again, given such a space, you just look at the locally constant functions on some space with that integer valued, I should say. That gets you an idempotent generated commutative ring. And conversely, Keinmal showed that every such ring has to be of this form for some space. Another one, which was, well, it was a bit earlier than Keinmal, but actually quite a bit more general, was to do with biregular rings. Okay, so he showed that, or they I guess showed that these are dual to bundles now of simple rings over certain spaces. So given such a bundle, you look at the continuous sections, right? And that will get you a biregular ring. I mean, this is not so important, but if you're curious, biregular just means that principal ideals are generated by idempotents. So again, it's the condition saying you have plenty of idempotents in some sense. So the sections would give you a biregular ring. And given such a biregular ring, you can always represent it on such a bundle. And this does actually apply to non-commutative rings, but in that case, it can be kind of trivial. So if you start with a simple ring, for example, then sure, you get a bundle, but it's trivial. It's just the ring over that point, right? So it doesn't really tell you much about the ring. So officially it applies to non-commutative things, but really it's not as non-commutative as you would really want. What about the other guys? Are there non-commutative extensions of, say, Gelfand and Keinmal, etc.? Well, yes, there are. So in the C-star algebra case, there are these nice results of Kunjan and Renaud, which say that instead of dealing with just a single C-star algebra, you look at a pair of C-star algebras. So one guy is non-commutative, and then some nice commutative subalgebra inside, a nice Cartan subalgebra. So Kunjan and Renaud showed that pairs of these guys correspond to now twisted, effective, locally compact Hausdorff et al. Groupoids. So again, given such a groupoid, you can always look at the basically the complex valued functions, modulo the twist, I guess, and that will give you a nice C-star algebra with a canonical Cartan subalgebra. And what they showed is that, in fact, every one of those is of this form. There is a bit of an issue or a question here about whether this can be made functorial. They created this nice correspondence between these objects, but didn't really look at morphisms. Whereas in these more classical commutative dualities, like Gelfand duality, for example, you also have a correspondence between the morphisms. Continuous maps on the one hand with C-star algebra homomorphisms on the other. right? In fact, to get general C-star algebra homomorphisms, you have to look at partial continuous maps. Okay, but here we don't, as yet, have anything like this. Some recent work of mine has started, showing how this can be made factorial, but in the original work, this was not yet done. As for Keimel's work, this also has a non-commutative extension, which was worked out very recently by this large collection of authors. I think it was 2 groups originally, but then they merged into this one massive group. So what they showed is that if you look at certain kinds of Steinberg algebras, right, which they called quasi-Cartan pairs of algebras, then again, you get a duality now with twisted, effective, ample groupoids. So ample just basically means locally compact, Hausdorff et al., and zero-dimensional. Right? And again, there's this question about functoriality. So they just had the sort of correspondence between the structures without looking really at what the morphism should be. But seeing this, there's a very natural question, right? So what about the next level? What if you wanted to get this more general duality of Peirce and Downs-Hoffmann and find a natural non-commutative counterpart of that? It's not too hard to define what a ring or even a ringoid over an ample groupoid, what that should be, what kind of a bundle you should have. And then from that, you can create an algebra or a ring at least. So that's easy, but the question is what are these things in a more algebraic, characterization, right? So what you would really like is a nice algebraic characterization of these guys, which then really allows you to show you again have this kind of duality. And maybe not just the algebra or the ring, maybe again, you might need some kind of pair, or maybe even more than a pair. Maybe you need, say, 3 or 4 little structures combined together to be able to get this nice kind of duality. So that's what I eventually wanted to talk to you about today. But first, I wanted to go through another kind of parallel series of dualities on lattices and semigroups. So there's a lot of dualities that trace their way back to this classic duality of stone between Boolean algebras on the one hand and stone spaces on the other. So just to give you a picture of all the various dualities that people have looked at, I mean, this is still going on even today, right? There are still results which are extending this very important classical result of stone. Right? More recently, people like Lawson and Kudryavtseva have looked at sort of bundle extensions of this. So here you have skew Boolean algebras on the left-hand side, where you have some kind of non-commutative meets and non-commutative joins. And these again correspond now to bundles of stone spaces, right? No algebraic structure really, just a bundle map from 2 stone spaces. And it's kind of non-commutative here, but to be honest, I think you would be able to recover this just from the order structure. So you could sort of, the non-commutativity here is maybe not as intrinsic as it appears. But soon after that, they did come up with some very truly non-commutative extensions of the classic stone duality. So there's this first one, where you have a duality between Boolean inverse semigroups and ample groupoids. And this was really done, I think, just by Lawson in 2010. But then with Kudryavtseva, they looked at a lot more general things. They looked at frames and quantum frames and things like that. And as a corollary, they had this more general version of this, where instead of inverse semigroups, you have Boolean restriction semigroups. And these correspond not to groupoids anymore, but ample categories. We'll talk about them soon. But then there's the natural question, well, is there some kind of analog of the Peirce-Downs-Hoffmann or some kind of non-commutative Peirce-Downs-Hoffmann theorem, but in this general context of semigroups? What would the semigroup be? It's not too hard to define what a category groupoid bundle should really be, and then you can look at sections. This will give you a semigroup, very nice, but what kind of algebraic or what kind of order properties really characterize the semigroups that arise in this way? And more than just an exercise in generalizing for the sake of generalizing, it would be really nice if you could actually use this to prove the ring theoretic results, right? The ring dualities. So up until now, these 2 sort of paths have been fairly disjoint, right? So in the ring theoretic worlds, you have access to ideals, and that's usually what people look at. Here we look at ultrafilters generally, and this is how you get these dualities. But wouldn't it be nice if you could maybe just use the ultrafilter versions of these results and actually get the ring theoretic results as almost just a corollary of this more general work. And that's what I wanted to at least outline for you today, how to fill in this gap here, how to characterize these semigroups, and then at the very end, use this to get a nice ring theoretic duality at the end. So first though, just to get started, to sort of ease your way into these things, I thought it would be better to quickly go over the very first classic stone duality. So to start with, let's take any old stone space. So just a zero-dimensional, compact Hausdorff space. So because it's zero-dimensional, we have lots of compact open sets, lots of clopen sets, right? And they have a very natural order structure, just inclusion. And we immediately see it has quite a number of properties, all the properties that you need to define a Boolean algebra. So the empty set, well, that's the smallest clopen set. The whole space, that's the largest clopen set. So it's definitely a bounded poset. You have your meets or infima come immediately from intersections. The union of clopens is again clopen, so that gives you your joins or suprema. Complement of a clopen is again a clopen, and these are indeed complements in the lattice theoretic sense, not just the set theoretic sense. And last but not least, they satisfy this distributivity condition. So this is, this is pretty obvious if you have unions and intersections, right? But if you have a general lattice, this is an extra property that really has to be stated explicitly. So that's the easy part, right? Start off with the stone space, look at the clopens, voila, you have a Boolean algebra. The hard part is really to go the other way around. So even before you get to going the other way around, it's good to ask yourself this very simple question. And that is whether, if you have a stone space, whether the resulting Boolean algebra really encodes that space, right? Is there really any possibility at all of recovering the space from the Boolean algebra, right? At this stage, you might imagine that you could potentially have two different spaces, right? The two different stone spaces, and yet when you look at the clopens, maybe they might give you the same Boolean algebra. Well, this doesn't happen. And we can see it by doing this little game, this little recovery result. So if you want to see how to recover the space, first you note that every single point corresponds to an ultrafilter of clopen sets. So you're just looking at all the clopen sets that contain a single point X. To see it's an ultrafilter, i.e. a maximal proper down-directed upset, you just note these properties here, right? So clearly the empty set doesn't contain X, so it's a proper subset. Anything bigger than something containing X, well, surely that also contains X, so it's an upset. Any two things containing X, well, their intersection contains X, so it's downwards directed. And finally, for maximality, just note that any clopen either contains X or its complement has to contain X. So that gives you the maximality part. Okay, so that tells you that, well, these points give you ultrafilters, but then the next question is, well, maybe there could be more ultrafilters, right? But no, even an abstract ultrafilter turns out to be always of this form for some unique point X. Right? To see why, well, you just take some ultrafilter of clopen sets, look at its intersection, right? Because it's down directed, that means that it has the finite intersection property. Compactness tells you, okay, it's not empty. Maximality tells you it can't consist of more than one point, so it has to consist of exactly one point, right? And then using the upwards directness, you can show that then U actually has to be exactly all of those clopen sets containing that point. In other words, this map you get from points to ultrafilters is a bijection from X onto all those ultrafilters in the clopen sets. Okay, and moreover, if you start looking at a clopen set, you'll see it gets mapped to all those ultrafilters which contain O, right? So X being within O is the same as saying O is within UX, right? That was the definition of UX essentially, right? But this expression is nice because this you can define abstractly, right? You can look at ultrafilters and just look at all the ultrafilters containing some fixed element. And that defines a very natural topology on your ultrafilters. And with respect to that topology, what this is really saying is that this map is not just a bijection, it really is a homeomorphism. Okay, so you really have recovered the space just from the Boolean algebra structure of the clopens, right? We've recovered it as the ultrafilter space. And this tells you really, or gives you a clue as to how you would start from a more abstract situation. You have an abstract Boolean algebra. Okay, right? Then you now define the points to be the ultrafilters, right? And you give them a topology just coming from this basis, looking at all the ultrafilters containing some fixed element. And once you identify your ultrafilters now with just their characteristic functions, then what you see is you end up with a closed space of this infinite product here of just those 2 points. And it's not too hard to see that this is a stone space, right? It's compact, zero-dimensional, right? And well, Hausdorff as well. And therefore, a closed subspace also has to be a stone space. So you've gone from abstract now to topological, right? And this is pretty much it, right? So this tells you that really Boolean algebras are dual to stone spaces by these two maps. There is, like I said, this issue of morphisms, right? We would like to also do the same with continuous maps corresponding to Boolean algebra homomorphisms, but I don't want to talk too much about that, not until much later. But at the object level, at the structure, you know, the level of just these Boolean algebras versus these stone spaces, then you do indeed have this nice duality. So we want to show you how to do something non-commutative. And again, before jumping sort of straight into the really nitty-gritty of what to do with groupoid bundles and things like this, right? I think again, it would be good to just review Lawson's non-commutative extension of the classic stone duality. And just a quick little intro, I have to tell you first what a groupoid is. So groupoids for us are not perhaps the groupoids you're used to. They're not, you know, small categories where all morphisms are isomorphisms. We tend to view them as just a single sorted structure, right? So as a group with many units, as some people like to say. What this really means is, well, A, we have a partial associative product on some sub-collection of pairs, right? All our idempotents here are in fact units. So that just means when the product is defined with a unit, it basically does nothing, right? It just leaves the element fixed. And last but not least, every element has a unique inverse, right? An inverse in the sense that if you multiply on the left or the right, you get a unit. And these conditions basically define you a groupoid, right? The bisections or slices play a particularly important role in this theory. So a slice or bisection is just a subset on which the range and source maps here are injective, right? So there are no two elements in B which have a common range or source. That's all it's saying. And you can see that the associativity of the product in G passes very easily to a product you would naturally define on the bisections, right? You just take the product wherever you can, wherever it's defined. If you happen to have two subsets of units now, so not arbitrary elements of your groupoid, but just the units, then you know the product in this case just corresponds to the intersection. And of course, it doesn't matter which way we take intersections, right? This is a commutative operation just on those particular subsets. And those particular subsets of the unit space are precisely the idempotents in your semigroup. So what this tells you is that idempotents commute. Another important property is to do with inverses. So every bisection has a very natural inverse, right? You just take the inverses of all the individual elements, so of this bisection. Right? So it's again a bisection, ranges become sources, sources become ranges, right? And you calculate these products and you see that, in fact, it is a kind of generalized inverse in this sense. We don't have a unit necessarily, but if you take these products, then you'll see it acts, B inverse and B inverse B kind of acts like a unit with respect to B inverse and B. These properties, so this together with the fact that idempotents commute, are exactly what define an inverse semigroup. So we have this nice inverse semigroup just coming from the bisections. Sure. Which one? There's a lot of B's. Which one?
We use the injective line.
Idempotents, injective. No. Okay. Yeah. So you're just looking at bisections. It just consists of all those subsets B on which R and S are injective. Does that make sense?
So it's arbitrary.
It's an arbitrary subset at the moment. I haven't introduced any sort of topology or anything. We're just looking at arbitrary subsets at this point. And this is a restriction because some elements of your groupoid will have the same range or the same source, right? Even though they're different. And we're just saying that a bisection is a special kind of subset for which that does not happen.
What's the category sense?
So it's just saying the range and the source, so you can imagine these as the range object and the source object. So the domain and codomain, I guess, would be the more standard term in a category, right? So you've got all these morphisms and none of them have the same domain or codomain, right? So that's all it's saying. Yeah. Okay, so we have this inverse semigroup, but this will only give you, in a sense, a very special kind of inverse semigroup. We'll talk about that in a second, but first I want to look at also the order structure of these bisections. So again, the natural order here would be inclusion, right? But the nice thing is that has a more kind of algebraic characterization in terms of the semigroup structure. So you can rewrite it like this: O is within N if and only if O is equal to O n inverse N. And this thing on the right here, that is the standard, or at least one way of defining the order in an inverse semigroup. Right? So it's saying that this canonical order that you can define on any abstract inverse semigroup, in this case, happens to coincide with just inclusion. Once you know that, well then you see that this inverse semigroup you have is then a meet semilattice with respect to the usual inclusion, right? You just take, your meets will just be intersections. Easy, right? However, unlike with Boolean algebras now, this is not a joint semilattice because the union of two bisections may not be a bisection. Right? You could have one element in O and one element in N, which do share a common source or range, right? Okay, so that's a little bit of an annoying issue. However, you can kind of get around this by saying, well, you do at least have joins of very special pairs. So some people would take special to mean compatible in some sense, but I'm going to look at even more special pairs, which are what I'll call orthogonal. So you can imagine this as a purely algebraic definition of orthogonality that would apply in any inverse semigroup. And any two guys that are orthogonal, in this case, with bisections, you can see that this is equivalent to saying, well, number one, they're disjoint, but also that their union is again a bisection. So in this case, orthogonal guys do have supreme, just coming from unions. Also, if you look at arbitrary idempotenents, then these do have joins, right? Just because any subset of the unit space is a bisection. So we don't have to worry about this problem we had before. And not only that, but they also have relative complements, just like with Boolean algebras, right? So a relative complement in the order theoretic sense would be written like this, okay? And because we know that meets are intersections and joins are unions, then we can see that these are indeed true. Okay, and again, because we're dealing with intersections, unions, we know everything is nice and distributed. So we do have these bisections do have a kind of Boolean structure, if you like. Okay, yeah, so they form what's known as a Boolean inverse semigroup. Okay, but next, I want to talk about, we need to introduce a topology, right? If we just looked at groupoids and we looked at arbitrary bisections, well, we would get not exactly the kinds of Boolean inverse semigroups we're looking at. We want to look at least. Okay, so I need to introduce topology. So there's a few different ways of defining this first notion of being a tile. The simplest, I think, at least, or the most relevant perhaps in this case, is to say that a topology on a groupoid is a tile if I can find some basis of bisections which is closed under taking products and inverses. Right? So it has a very kind of algebraic character, or in a slightly different way, you could say that all open bisections form a basis for the topology, which is also an inverse subsemigroup of the collection of arbitrary bisections. And a more, I guess, kind of more standard topological way of rephrasing this would be to say that all of your operations here, the source map, the range map, the inverse, the product, where it's defined, have to be both continuous and open maps. And well, it turns out they will also be locally injective and hence local homeomorphisms. That's probably the usual way people say it, but this is another equivalent. And there are various results about, if a couple of these maps happen to be continuous and the other is open, then in fact they all have to be continuous open, these kind of things. But in the end, they all end up being continuous and open. What about ample? Well, this is pretty much the same idea. It's just instead of looking at open bisections, you look at compact open bisections. Right? So, and we're going to just assume things are Hausdorff just to make things easy. Some people would not take this as part of the definition of ample, or they would just assume that the unit space is Hausdorff, but we will just assume the whole groupoid is Hausdorff with respect to this topology. So assume we have a Hausdorff topology. Ample just means we have a basis now of compact open bisections, which is again closed under inverses and products. Equivalently, this you could say that arbitrary open bisections. These form a basis for topology and an inverse subsemigroup of within this collection of arbitrary bisections. Okay, and again, if you want a more topological characterization, it's saying the same thing above. It's saying a tile as well as zero-dimensional and locally compact, and still Hausdorff, right? We're assuming that from stuff. And now we know when we look at compact open bisections, we again have the relevant operations. They're closed under the relevant operations. They're definitely closed under intersections because we're dealing with compact open, not just open, and we also have these complements. Orthogonal elements also have unions, right? So the upshot being that these compact open bisections again form a Boolean inverse subsemigroup. So the idea is that the topology is allowing you to get a more interesting class, I guess, of Boolean inverse semigroups, right? Before we were only looking at essentially the discrete topology, but when you add in a topology, then this allows you to get a nicer class of Boolean inverse semigroups. Okay, so that sort of does one direction, right? Given an ample groupoid, you have a Boolean inverse semigroup, just like every stone space gives you a Boolean algebra. What about the reverse direction? How would we define a Boolean inverse semigroup from some, how would we define an ample groupoid, sorry, from some Boolean inverse semigroup? Well, again, you use ultrafilters. So we have this canonical ordering, remember, on any Boolean inverse semigroup. And so we just look at the collection of all ultrafilters with exactly the same basis as before. This time, however, we also have a product on our ultrafilters, just coming from the product in the semigroup. Right? The only slight issue is that if you take a product of two ultrafilters and you look at all of those individual products, may not be upwards closed. But to fix that, you just take the upwards closure, and it turns out it's not just an upset, it's not just a filter, but it will again be an ultrafilter. So long as 0 is not already a product in UV. Right? So this is why it's a groupoid. The product is only partially defined. It's not defined for all ultrafilters. And when you do that, you see that these basic open sets that you used to define the topology, that they're in fact now compact open bisections. Okay. And you also immediately see that this collection of basic open sets is closed under inverses. It's also closed under products. So with that characterization we had, this says that yes, this is indeed an ample groupoid. Okay. And the last question, which we sort of glossed over, I guess, is whether it's really the right ample groupoid. I mean, you could just assign the exact same ample groupoid to any Boolean inverse semigroup, but that's not going to be interesting, right? To know that it's really the right one, you have to show that if you happen to start with an ample groupoid and then look at the semigroup and then look at the ultrafilters, this should recover the ample groupoid that you started with. And indeed it does. It's the same as before. So given any point, look at all the compact open bisections containing that particular point G, and note that this is going to be a bijection. With this topology, it'll be a homeomorphism. And now in this situation, it will also be, in fact, a groupoid isomorphism. Right? It respects the inverses, it respects the products. So it's the right thing to choose. And then you have now essentially this duality due to Lawson. So again, I should point out, also did more than that. He also showed that the morphisms are dual. But at the moment, we're just concerned with this duality between Boolean inverse semigroups on the one hand and ample groupoids on the other. So is everything clear? Does that all make sense? This was the easy stuff. So now we're going to get serious, right? So now we're actually going to, well, actually, no, before we get serious, there is one more thing I wanted to point out, right? So just, you can forget about everything else for the moment and just think about abstract inverse semigroups. Right? I just wanted to mention this correspondence you have between inverse semigroups with meets or infimum and those with an expectation. So first note that if you have an ample groupoid, you look at its compact open bisections, then every one of those contains a maximal idempotent. You simply take the intersection with the unit space, right? So that's easy. But the next thing to note is that even in an abstract inverse semigroup, you can do sort of the same thing. You can take any element, and as long as you have meets, I should say, then you can define this function phi like so. And with a little bit of theory, you will find out that this is, again, the maximal idempotent below A. Leach observed that the converse is also true, in the sense that if every element has a maximal idempotent, then in fact you can define meets using this function phi here. Okay, so they're really just two sides of the same coin. And Leach also noticed that this phi you get has these nice properties, which if you're a C-star algebraist, you might get kind of excited because these are the same kind of properties we deal with expectations onto Cartan subalgebras. So it's an idempotent map, and also it's a sort of bimodule map, right? As long as E is in the range of phi, well, then you can always take it outside. There's a couple of other properties which I guess Leach didn't note exactly, but these turn out to also be important. So one is that it's what I would call shiftable, meaning that if you have this product ABA, it doesn't matter whether you apply phi to the first two guys or the second two. It's exactly the same. And it's also what I call bistable in the sense that if any product is within the range of phi, so it's an idempotent, then again, you can apply phi to either the first guy or the second guy, and you'll still have an idempotent. Fairly simple conditions, not too hard to verify, but they turn out to be quite important later on. So these will play a much greater role when we deal with more interesting objects. Okay, so as I said, we want to now actually get to the interesting new stuff, right? So the first thing I have to introduce now is ample category bundles. So again, we're going to take a rather strange view of categories. We're not going to view them as objects and morphisms. We're going to view them as one-sorted structures, kind of like we did with groupoids, but we just don't have inverses anymore. So what does that mean? Well, on the one hand, we again have a partial associative product, so defined on some pairs. Each element has to have a source and a range unit, right? Which also determines when the product is defined. So the product of two things is defined if and only if their source and range match up, I should say. Okay, and so this is all you need to define a category in this one sorted sense. Again, a topology is a tile if all these maps here happen to be continuous, open, and locally injective, i.e. local homeomorphisms. And another thing I have to define is what I call an iso cofibration. Well, this is not really my term. It's very weird, but this is apparently what some category theorists refer to it as. So it's like a functor between categories, except that so a functor would say that this is true whenever the product AB is defined, right? A iso cofibration is saying it's true also when the product of row A and row B is defined. Right? So it's sort of mapping composable pairs to composable pairs and vice versa. Right? That's all it is. And now I can define what an atile category bundle is. So it's simply an open, continuous iso cofibration, special kind of functor, right? From one atile category to another atile groupoid. Now. So this is, well, that's the bundle, right? I want to get from a bundle to a semigroup. And to do that, I have to consider sections. A section is what you would expect. It's just a continuous map from the groupoid to the category, which is a right inverse for the bundle map itself. Right? And I will want one very special kind of a section I will call a zero section. So it's just one that absorbs basically products whenever they're defined. Okay, if your bundle here has a zero section, each fiber has invertibles. So even though C itself is not a groupoid, this is saying it has a very large subgroupoid. It has a subgroupoid which maps onto the entirety of G. That's all that's saying. And last but not least, if G is an ample groupoid, then I'll call this an ample category bundle. So maybe the reason for these little extra conditions here may not be clear at the moment, but they will become clear very shortly. So just keep this in mind as the definition of an ample category bundle, a very special kind of a tile category bundle. Okay, so how do we get to semigroups? So take your ample category bundle. Because we have this zero section, we have a very natural notion of the support of an element, right? So all all the elements in the groupoid which don't get mapped to the zeros in the fiber. If the support of A or B doesn't actually have to be both, at least one of them is a slice or a bisection, then we have a well-defined product between those two sections. So it just takes any G to the product of the corresponding elements of or values of A and B. Right? And you need to be slices here because otherwise, this G could potentially, be at the form HI for various different H's and I's. Being a slice ensures that does not happen, so that this is still well-defined. Just note also that the support of a product is compact when the supports of A and B are. In fact, the supports here I should maybe mention are always closed, which is a bit weird. You're probably used to thinking of supports being open. But because we're dealing with sections of an Untitled bundle, that's why the support is always closed. Right? Okay. So what all this really says now is that under this product, these compact slice supported sections form a semigroup. And then your natural question, if you're trying to look for a duality, is can you recover the bundle from the semigroup? Right? If you really want a duality, the answer to this should be yes. But unfortunately, the answer is definitely no. Right? There's a very easy example. So I think the easiest, I guess, would be to take any old finite discrete group. And any homomorphism of that onto some other finite discrete group will basically define a bundle once you add zeros in all the appropriate sections. And the sections, the compact slice supported sections will then just basically give you a copy of the group you started with. So whatever, start with some group, consider all these various different homomorphisms, they'll give you different bundles, even though the sections, the semigroups you get will be the same. So that tells you that, well, this cannot be done. You can't recover the bundle. So what do? Well, what it really just tells you is that you haven't got quite enough structure. And if you're a C-star algebraist, for example, you know what kind of structure you probably need. You probably need a special kind of sub-semigroup, right? Or maybe even a special expectation onto some sub-semigroup. Maybe that will give you the real extra structure you need to recover the bundle. Okay, so we need some extra algebraic structure. And what would you expect it to be? Well, of course, we want an expectation. So there's a very natural expectation you can define on the compact slice supported sections. Right? Because you're dealing with a nice bundle, it's housed of, the unit space should be a Clopin set, so you can essentially restrict to the unit space. I mean, it's sort of, I guess it's not a restriction in the usual sense because they are defined outside the unit space, but you're just setting them all to be zero. Okay, and you can do some elementary algebra, check that this defines an expectation, that it's also shiftable. But this is alone still not quite enough to capture the bundle that we want. We still need a little bit of extra structure coming from some further sub-semigroup of the range of our expectation. But again, there's a very natural candidate for what to choose. You just look at basically all the characteristic functions of Clopin subsets, or compact open subsets, I should say, of the unit space. Right? So all those sections whose values are or non-zero values lie completely within the unit space of C. Right? So that the units in C always lie within the unit fibers of G, right? So what that tells you is that the support of A in such a thing has to lie within the unit space. That's fairly clear. And these guys, and from that, it should be clear that these guys always commute with anything else which is supported on the unit space. Right? Right? So Z here can take either a zero value or a unit value. Either case, it's either setting the value at A to zero or it's leaving it fixed. So it doesn't matter which side you do it on, right? So all this is telling you that this special, characteristic sub-semigroup, maybe you would call it that, lies in the center of the range of the expectation. It won't lie in the center of the whole thing, right? Because these functions which are supported outside the unit space could be different, right? When you multiply by a unit on the left or a unit on the right. But it is at least central in the range of the expectation. And these properties I mentioned before also come in handy. So this is also a bistable subsemigroup, in the sense you have a product lies in that. Doesn't matter if you apply the expectation to either element in the product. And it's also normal, just in the usual sense of semigroups, which you can see generalizes the usual notion of normality in a group, right, or subgroup. So we have all these properties, and together they define what you might call a well-structured semigroup. So, I mean, the precise properties, not so important, just the key idea is that we've extracted enough algebraic structure from these triples here to really, not quite maybe characterize the things that arise from this, but at least give us a much better idea of the kinds of structures we're dealing with. So it's a good first step. We still don't actually, to be completely honest, have enough algebraic structure. We will add a little bit more in a second, but this gives at least something to play with, something to start with. So let's look at order structures. So let's start with a well-structured semigroup. Here, unlike with inverse semigroups, there's really two quite natural or quite useful orderings you can define. Right? The first one is defined in much the same way as you would usually define the order in inverse semigroup, except instead of using projections, we're using this special subsemigroup Z, right? Which you might call the projections. Right? Okay, and so one order just says that A is kind of a restriction of B, in the sense you just multiply by one of those special projections to get A. The other one is more like what I would call domination. So it's a little bit nasty to state in all of its gory detail, but maybe what's the best way to explain it? I mean, the stuff on the right is kind of clear, right? So to say that A is equal to BSA is equal to ASB, it's just saying that SB, BS, they're kind of like local units for A on the left and on the right. Okay, which means that B and S are kind of like inverses, at least on A, with respect to A in some sense. Right? The extra conditions here about AS and SA lying in the range of phi and BSSB lying in Z, these just sort of ensure that the supports, if you're imagining these as functions, it sort of ensures the supports match up kind of nicely. So if you have an inverse semigroup and an inverse semigroup with meets and phi is the canonical expectation, Z is the idempotence, well, then in fact, these two orders are exactly the same. They're just the usual canonical order in your inverse semigroup. That's easy. But in the situation we're interested in, where you have some ample category bundle, and you're looking at the resulting well-structured semigroup, then for any two sections supported on compact slices, you find that this really does correspond to a kind of restriction. It's really just saying A and B are exactly the same on the support of A, the smaller guy. Whereas this, on the other hand, does correspond to some kind of domination or inclusion. It's just saying that the support of A is definitely included in the support of B, but even more, it's actually included in this sort of inverse support, if you like, all those elements which take invertible values under B. So these two, I mean, you can think about it for a second, but it's not too hard to imagine these two could now be quite different relations, right? And in fact, you can say a bit more that if A is a restriction of B, because of the nature of this tile bundle we're dealing with, that in fact they would have to agree not just on this compact subset, but in fact on some open subset containing that compact subset, some clopen subset, in fact, because we're dealing with an ample groupoid, remember. And what that means is that you have a natural way of defining relative complements. So I'm trying to give you this picture that there is some kind of Boolean structure going on as well. Right? So all you do is if you want to define the relative complement of A inside B or relative to B, well, you just let it be equal to B everywhere except on the support of A where you just set it to 0. Well, you know this is again a continuous section due to this fact up here that they must agree on some clopen set. When you're dealing with continuous functions, you can always take a partition into two clopen sets, and you can replace one of those restrictions with any other continuous function, and the whole thing will again be continuous, right? So you're free to play around with things like that. What else to note? Another important thing to note is that every element is dominated by some other element. So if you want to know why, well, what you have to use is the fact that this is compactly supported. So, I mean, I can say the argument for you, right, basically here is like, okay, take your A has compact support. For every element in the support of A, I know the fiber has to contain some invertible element. This was part of the definition of an ample category bundle. Okay. So that means I can have some section which has invertible values, in fact, in some neighborhood of that point. Right? By compactness, I can do this finitely many times, and I can actually cover A. By ampleness, I can make sure that the supports are disjoint, and then I just stick them all together into one big function B. And that function B will then dominate A. That's the idea. Okay. So to get a bit more Boolean structure, I need to again define a kind of orthogonality. So take a well-structured semigroup and let's define orthogonality like so. So A is orthogonal to B if I have basically left and right units for A which annihilate B, right, on the left and right respectively. So for inverse semigroups, again, this corresponds to the usual notion of orthogonality. For ample groupoid bundles, it does what we want it to do, right? So for ample groupoid bundles, if you take two sections, they happen to be orthogonal, this is exactly saying that the supports are disjoint and the union is again a bisection or a slice. Because again, we have this issue, right, that you don't have arbitrary joins. You can't just take two functions which might happen to have, different non-zero values on their supports and join them together in some way, right? This is not possible. However, it is possible as long as they're orthogonal. Then you really can define a join in the way you would expect. Namely that you want it to be equal to A on the support of A, you want it to be equal to B on the support of B, and zero everywhere else. So we again have these restricted suprema, and again, it's to do some elementary calculations, you'll find it's distributed wherever the joins actually exist. Okay. And last little thing to note is that again, if you have two projections in this special sub-semigroup, right, then their join is again a projection, right? If this only takes unit values on its support, well, then the same is true of the join. Easy. So there's a lot of properties here, but they're all fairly simple algebraic properties that once you've seen enough, you can sort of get used to. So let's do maybe a quick review of all these various properties. Let's put this in the definition. So remember we talked about well-structured semigroups. So a well-structured semigroup is a special kind of triple semigroup, sub-semigroup expectation which satisfies these conditions. Right? So S is a semigroup, phi is a shiftable expectation, Z is a normal bistable sub-semigroup of idempotence, which lies in the center of the range of the expectation. This is all stuff we already kind of showed, right? Like, so this is nothing new. I'm just trying to summarize it all in a nice little definition. And let's talk about those extra properties, right? And let's call these things Steinberg semigroups. So as long as every element of S is dominated by something else, as long as Z has a zero, so we can define orthogonality, and as long as S and Z both have not arbitrary suprema, but they do have ortho suprema, which are distributive and which they also have these relative complements. So these are all the conditions you need to define some kind of algebraic structure we'll call a Steinberg semigroup. Right, this is what we've shown. From ample category bundles, we always get Steinberg semigroups in this terminology. Maybe just one little thing to point out here is that I'm assuming G is Hausdorff, right? That was part of the definition of an ample category bundle. However, I never said anything about C being Hausdorff, and that's not an oversight, that's how it's meant to be. But there is, if you really do want to restrict yourself to Hausdorff categories, then that's not too hard because there's a simple algebraic way of characterizing when this occurs. So the total category is Hausdorff precisely when each of these compact slice supported sections has a support projection. So where there's some sort of minimal left and right units for A. Okay, and so when this happens, that means that you have what Kudryavtsev and Lawson call a restriction semigroup. So what we're doing here is more general than what they did, at least when you look at their work, what it means for Boolean restriction meet semigroups. So to be honest, even when you do have support projections, we have a kind of more general structure here because we have this extra data coming from, the expectation, for example. But I think the key difference is that we're not requiring any kind of support projections, whereas for restriction semigroups, this is a very intrinsic part of their definition. So what we're doing is quite a bit more general. So the next question, of course, we want to set up a duality. We're hoping that this Steinberg semigroup thing that we've created, we've defined, is really characterizing the semigroups we get from ample category bundles. Right, so the first question to ask to verify this, to show that we can get a duality, is can we recover the bundle from the Steinberg semigroup? And indeed we can. So how do we do that? Well, as before, we use ultrafilters, right? So we immediately have an isomorphism from the groupoid that forms the base of the bundle to the groupoid of ultrafilters. This time it's, I guess, a little bit different to before, right? It's not all the, you don't look at all the clopin sets containing G, you look at all the sections whose value at G happens to be invertible. So this gives you an ultrafilter with respect to the domination relation, I should point out. So sometimes you need to use restriction, sometimes you need to use domination. In this case, I'm referring to domination. That recovers the base space, but then what about the rest of the bundle? What about the fibers? How do you recover them? Well, note that if you have two sections which have a common value at some G, then again, because we're dealing with the tile bundles, they actually have to have the same values within some neighborhood of that G. And what that tells you is that there is actually yet another section which is defined in some neighborhood of the inverse of G, such that these two expressions are now equal. And you can see again that this is a sort of purely algebraic condition. We can use this, we can take any ultrafilter and define this condition here, and that will give you a kind of equivalence relation. And that gives you a hint as to how you should recover the fibers of the bundle. Right? Once you give them again an appropriate topology and a product and everything, then indeed you can recover the bundle. I won't go into the details, but trust me that is true. So okay, we're okay with recovery. We know that there is at least some hope we can turn this into a duality, and this sort of gives you a hint as to how it might go. So let's try and do that. So take now an abstract Steinberg semigroup. Again, look at ultrafilters. Again, these form a groupoid. You might be curious as to what the inverse should be now, because we're not dealing with inverse semigroups. There is no way I could just take inverses of individual elements. What I instead do is I take basically the witnesses for the domination relation. So all those elements in the ultrafilter, if there is something greater than that via this S, well, then you chuck S into this inverse ultrafilter. That's the idea. So we still have an inverse. We have a product defined in exactly the same way. And now we define this equivalence relation I mentioned on the previous slide. So we just say that A and B are equivalent at U if I can find some element in the inverse ultrafilter, right, such that these two expressions are equal. And now to define the rest of the bundle, you look at these pairs, right, consisting of an ultrafilter and some equivalence class at that ultrafilter. So these form a nice category under the product you would expect. I mean, this is obvious. You have to check that this is well defined, right? You have to check that if I replaced A and B with equivalent elements, that I would still have something in the same equivalence class, right? So there is stuff to check here, but this can indeed be done. As long as, again, 0 is not within UV, right? This is only a category. The product isn't defined everywhere. It's only defined when the source of U and V match up, right? Okay, and the bundle map in this case is now very easy to define, right? It's just the canonical projection. Right? As long as you give these pairs the appropriate topology, kind of like what we did before, right? So we'll have the inverses of the basic open sets of the base space, right? We want this to be a continuous map, right? So we have to definitely include these in our topology. And we also include these kind of tubular neighborhoods where look at all the pairs containing some fixed element of your semigroup. So with respect to that topology, this row does indeed give you an ample category bundle. These pairs do indeed form an Untitled groupoid, an Untitled category, right? And the map row then is then an open continuous map. And an ISO cofibration as well. Okay, so that gets you that gets you sort of one direction in a sense. You've got the bundle now. Right? The only problem is we don't know if the semigroup we started with could actually be represented in the way you want. We don't know if that really does correspond to sections of the bundle that we've constructed. So this is what we have to show. So take a semigroup, sorry, Steinberg semigroup, and look at the ample category bundle that we just defined using ultrafilters. And now note that every element of the semigroup defines a function on the ultrafilters in a natural way, right? You just map every ultrafilter to the corresponding pair. And because of the way we define the topology, because we defined it using these tubular neighborhoods, these functions are indeed all continuous, right? And they're clearly sections, right? But they're also continuous. And when you look at the products defined on the semigroup, right, on sections as we did before, then this gives you indeed a semigroup isomorphism from S onto the entirety of this guy here, right? I mean, yeah, I mean, the fact that it's, let's see, the fact that it's faithful, I guess, really comes from the fact that everything is dominated by something else, right? This tells you that the expectation has to be non-degenerate, which then tells you this has to be faithful. As for why it has to be onto the entirety of that semigroup, well, that's where these orthosuprema came in. Without those orthosuprema, you wouldn't be able to show that S maps onto that. It could have been a strict sub-semigroup. So all these conditions come into play for proving this result. You also notice that, again, it maps this sub-semigroup projections onto the sub-semigroup Z onto the entire sub-semigroup of projections or unit-valued sections, and that it also respects the expectation. If you like, the abstract expectation you started with becomes the canonical expectation by restricting to the unit space. So all of this structure of the original Steinberg semigroup is really preserved in this representation. And finally, this gives you the result we've really been chasing, right? That again, you do have this duality between Steinberg semigroups and ample category bundles. So that's what we want. So now let me finally just briefly tell you a little bit about morphisms, right? Because this is one of the things I kind of advertised in the abstract, that this is not just a correspondence like with some of this previous work of Armstrong et al. It really is functorial as well. So first we have to think about what the morphisms could be. Well, the Steinberg semigroups, it's pretty clear what they should be, right? They should be semigroup homomorphisms. And they should also preserve this extra structure, right? They should preserve the expectation. They should preserve this special subsemigroup Z. And because joins are kind of important, they should also preserve the joins whenever they exist. They don't always exist. So we'll call this a Steinberg morphism. Whenever you have a Steinberg morphism between two Steinberg semigroups, this very naturally induces a continuous functor in the opposite direction of the ultrafilter groupoids. Right? All you do is just take any ultrafilter and look at the pre-image. Again, there's this issue of that, well, maybe it's not upwards closed, so you just take the upwards closure. And part of the theory is saying that whenever this is not empty, that this upwards closure is again an ultrafilter. It is a well-defined map from ultrafilters to ultrafilters. Okay, so it's a partial map, but it's well-defined, and more than just being continuous, more than just being a functor, it's also star bijective. What this means is that it maps stars to stars, right? A star in a groupoid is just the collection of all, arrows, all elements which share a common source or a common range, right? Depending on whether you're talking about left stars or right stars. And this is a very important condition because when you're dealing with semigroups and C-star algebras, etc., defined from groupoids, functors between the groupoids are not enough to ensure that you get morphisms between the C-star algebras or the semigroups. You really need this extra star bijectivity condition. Other authors use various names like, I don't know, covering functor or factor groupoid map, I guess, or algebraic morphism or Zakrzewski morphisms, etc. But star bijective seems to be the most natural one for me. So that's great. You've got a morphism between the bases of these two bundles, right? So you've got these two ultrafilter bundles defined from these two Steinberg semigroups. But what about the other fibers? Do you also have a morphism between them? And you do, but it's a little bit more subtle than that. you first have to use this map between the base spaces, take a pullback bundle, and then you have a fiber-wise map between that pullback bundle and the other bundle. And so it's a kind of a complicated two-step construction, right? The right morphisms in the category of these bundles here are not just single maps, but they're really pairs of maps. One is a map between the base space, the other is a map between the pullback relative to the first map onto the other, the fibers of the other bundle. So it's a little bit complicated, but these are the same, essentially the same kind of morphisms that Peirce was considering way back in the late 60s in his work, right? So these are a natural analog. We just have a bit more structure to take care of because our bundles also have some algebraic structure, right? They're category bundles, right? Okay, so essentially, I guess, there's also the other direction. You want to show Peirce morphisms give you semigroup homomorphisms or Steinberg morphisms, etc. But this all works out. So when you take these morphisms and you form the appropriate categories, you do indeed get an equivalence of categories. So it is really a truly functorial categorical duality with respect to probably the most natural morphisms you could consider. You have a question? Well, I mean, it's a matter of taste whether which direction you take the morphisms. Because especially in this case, because you have two maps, right? These Peirce morphisms. One is a map from the base spaces going that way. The other is a map fiber-wise from the pullbacks going in the opposite direction. So if you have two maps going in opposite directions, which is the more important one? Which is the right direction for your category? So, but yeah, you're right. If you want, you could call it you could switch the morphisms direction and say it's a duality of categories, not an equivalence. Right? You get both, I guess. Yeah, exactly. And so this is pretty much the end of the story as far as semigroups go. But remember, the original motivation was really to deal with rings, right? This was meant to be, in a sense, just a tool to get you the ring theoretic results. So let me again just briefly outline how you jump from semigroups to rings. So let's start again and let's define what an ample ringoid bundle should be. So it's the same as an ample category bundle, except now the fibers also have some additive structure. They all also form abelian groups. Okay? And the additive structure also should be compatible with the product when it's defined, right? So you should have this distributivity like you would expect. And then that allows you to define the product of arbitrary compactly supported sections. Now we don't have to just restrict to sections supported on bisections. Now they can be defined on larger compact subsets because we can just take the sum over all the h's and i's for which this is true, right? And we know this sum is always finite because A and B are supposed to be compactly supported. So any element which is compactly supported can be written as a finite sum of slice supported guys. This is a sort of standard lemma when you're dealing with the tile group limits. And the next thing to note is that your expectation also immediately extends to these more general sections, right? Again, all you do is you just restrict to the unit space. And it's not too hard to see. Things won't be dominated anymore, right? Not these larger guys. However, you will still have this non-degeneracy condition for your expectation, which will be important. And all these basically tell you have a Steinberg ring, which is exactly like a Steinberg semigroup. It's just also sitting within some larger ring. It generates a larger ring. That's all that's really saying. So it's very close to being most of the nice algebraic conditions that you need to define a Steinberg ring are already contained within the definition of a Steinberg semigroup. So how do we go from Steinberg rings to ringoid bundles? So take one of these quadruples now, these Steinberg rings, look at the ultra filters on S as before, right? Define your equivalence relation as before, but now we can define it on this larger ring as well. We don't have to restrict just to the semigroup. And that's important because we want to use additivity here. We want to use the fact that phi is additive to show that this equivalence relation now is also additive. That's not too hard. And then once you've got the additive structure, it's not too hard to check that this gives you now an ample ringoid bundle, I should have emphasized. Okay, and that because phi is non-degenerate, again, this map is faithful even on the entirety of the ring, not just on the semigroup. And it preserves all the relevant structure, right? So the representation you get from here represents the entirety of A on the entirety of all those compactly supported guys. And so instead of joins here, you have sums, right? This is what you use to make sure this is onto. Likewise, the special sub-semigroup gets mapped onto the compactly supported, compact slice supported sections, and likewise here and here, right? So everything is preserved under this representation, just like before. And again, morphisms are just like before, but you also, of course, require them to preserve the additive structure. So for the bundles, these Pierce morphisms should preserve the additive structure of the fibers. For ringoids, for Steinberg rings, I should say, the maps should not just be semigroup homomorphisms, they should be ring isomorphisms, ring homomorphisms, right? So as long as you just do everything additively, basically, then it all works out. So it's all the hard work has really already been done for the semigroups, right? Just adding the extra additive structure, checking it all works out. That's actually not too hard. So that gives you the final results, which I wanted to say, which is Steinberg rings are dual to ample ringoid bundles, right? In a truly categorical sense, like we had before. And that's it. That's it, folks.
So do we have any questions? Audience here or online?
Yeah. Can you hear me? I'm Enrique.
Hey, how are you?
Yeah, we can hear you.
Okay. Just in order to clarify my mind after your talk, I like very much what you did. What you're doing, it's abstracting the notion of a twisted groupoid algebra, and then what you obtain is that the dual is the ample group ringoid bundle that plays the role of a Cartan pair. Is something like that? What?
Yeah, exactly. I mean, I was trying to do most things at the semigroup level, but yeah, this is kind of like the Cartan subalgebra, this Z here. But it's a bit of a Well, it's a bit of a debate. Is it really Z or is it the range of phi, right? If the range of phi could be strictly bigger than Z. So which is the Cartan, I'm not really sure, right? In the more classical situation, this is the range of phi, right? But yeah. And this semi in the more sort of Cartan pair way of doing things, this semigroup doesn't appear at the beginning, it appears sort of after the fact as the normalizers of the Cartan, right? And all I'm saying here is that actually maybe it's better to forget about trying to define this from that and just take it as given from the beginning. And the advantage of doing that is you don't have to place any restrictions on the underlying groupoid. So this all works perfectly well even for non-effective groupoids. Whereas if you do it the more Kumja-Renaud way and you define this to be the normalizers, well, that only works with effective groupoids.
I see. Okay. Thank you.
Yep, thank you.
Yeah, so I just want to ask, this domination relation, is it in any way related to this P-set equivalence of open projections? Just vaguely remind me.
Yeah. I mean, there are various things which are. I guess it's sort of related. So let me see if I can go back and find where it is. So, no, it was a bit further over here, right? Okay. Sorry about this. Where was it? Here it is. Okay.
Yeah.
So on the face of it, it's not exactly defined algebraically like the PZ equivalence, but I think it is. Is it trying to encode the same thing? This is really trying to encode, if you like, compact containment. You don't really see the compact containment business here so much because we're dealing with an ample groupoid. So things are often defined already on compact or Clopen subsets, right? If they're already defined on Clopen subsets, then compact containment just is containment, right? So it's not as easy to see here. But yeah, it was PZ equivalence. It's more like, I guess, the way below relation you would define from Kunz below, or you can look at this the Kunz semigroup and then complete it, and you have this complete lattice or complete group, and then you can find this way below relation, right? Okay, and that is really trying to encode compact containment, and this is exactly trying to do the same thing, but just in a slightly different context, right?
Yeah.
Does that make sense? Yeah.
Yeah. I was just kind of wondering whether, like the Kuhn semigroup and maybe the Kuhn semigroup of a hereditary subalgebra would be one of these well-structured semigroups somehow. But then I don't know what the expectation would be. Right? Cutting down into the corner.
Yeah, yeah. I mean, the problem with arbitrary hereditary subalgebras or arbitrary open projections is that they may not lie within the normalizers, if you like, or this sub semigroup S, right? So this is why, yeah, this is why it's not, there's not an exact analogy, I think, but definitely it's sort of the same kind of idea, right? You're trying to encode some kind of topological relation, but in a purely algebraic way, right? Yeah. Thanks. Other questions?
Any chance of doing this outside the ample picture?
Yeah, well, definitely. I mean, this was sort of based on some preliminary work I did for the main stuff I wanted to do, which was really generalizing the Kuhn-Monod theory in the C-star algebraic setting. So this is kind of an algebraic analog, but yes, you can indeed do some very similar things and actually get basically unify this Kuhn-Monod work with this other work of Downes and Hoffman. So Downes and Hoffman appeared at the start here, and they did both as well. They first looked at an algebraic kind of situation, but then they also later looked at C-star algebras and their centers or whatever. And you can again do similar things. I mean, it's a little bit more tricky because well, then you don't have any projections floating around, right? Without ample. So in that case, this domination relation sort of plays a much more important role because you may not be able to get a projection in between A and B, but you can still somehow define what it means for A to be compactly contained in B, right? Yeah, I mean, yeah. And then there's also other things you have to take into account, like the norm and showing that the representation actually does give you a function which is sort of in the closure of the compactly supported guys and all this kind of stuff, right? So it's a lot more technical stuff to take care of, but the same ideas apply. Yeah.
So ample is like 0 dimensional.
Yep.
Right. So yeah, I was kind of also wondering, possible to incorporate higher dimensions in whatever the sense that means, you know, maybe paying attention to the way open sets intersect with each other.
Yeah. Well, it's really, in that case, compact containment becomes much more important. So this domination, I mean, if you like, think about this domination relation. Think about what it would mean if you just had some, let's say, commutative semigroup S, right? And Z was equal to S. So then this stuff over here just becomes unimportant, and all you have is this relation over here, right? So you could in particular consider a commutative C-star algebra under this relation here, that A is equal to ASB, right? For some S. And if you think about what that's saying, it really is saying that, you know, you've got some function A, and then you've got some S and B, which are inverse to each other just on the support of A. And in particular, that means this support of B has to compactly contain the support of A. And Milgram was, I think, the first to do something kind of similar in a kind of C-star algebraic way. He showed that you can recover the space, some locally compact Hausdorff space, from the continuous functions vanishing in infinity, let's say, but only with the product structure. You don't need the C-star algebra structure. You don't need the norm. You don't need the sum or the scalar product. All you really need is this product because it allows you to define this domination relation. Yeah. Yeah, no, it's definitely I was perhaps even more interested in the non-ample case, but this was good, a kind of good practice, if you like, for actually going harder for even the non-ample stuff, right?
Any further questions?
All right, if not, then we'll thank Tristan again. And just also advertise next week's talk which will be by Rocco, probably just butchered that last name, from the Université Libre de Bruxelles, and he will talk about the integration problem for Lie algebroids. And I should also mention that at the moment, I'm claiming we're going to get to talking here, but it might actually move because YesSwap has a conference on that week. So we might be in for a meeting. I will
Right.
let you know.
However, I am responsible for the schedule, so maybe I can wiggle it so that it doesn't coincide. So.
Thanks, and see everybody next week.